Last week we ended up, we want to finish off the adaptive nature of the box. Now, for your boxes that you're turning in, they didn't have to be adaptive because you're only building one box. So you did not have to do it this way. But I just wanted to show you these tools because they're fairly powerful. This idea of adaptive parts that move together, and then also building parts off of other parts in assemblies. It's a powerful tool. So I wanted to finish that up. Let's go ahead and see. It would have been nice if I saved it. Let's see, what can I do here? Let's pull up. I may just have to show you instead of building it. So I didn't start from the beginning. But last time we had finished off the building the female part off of the male part in an assembly. And so when we went to go change the dimensions, they should change evenly. We could test that. It may not work on this one. Let's give it a test. So let's open up the male part and let's change his dimension. So we'll change under this base flange, we'll edit the sketch and change our dimensions. So instead of a 3x8 box, let's do a 4x8 box. How about that? That's not big enough. We won't notice. Let's do a 7x8 box. How about that? And then we want to go back to our assembly and rebuild it. See that change? Let's rebuild it. And you see the female auto updates. So that's that idea of an adaptive part. It's pretty cool. Now the last issue with that is these holes. Okay, we want these holes to line up no matter what. All right. So in order to get the holes to line up, anybody have any ideas of how you would adaptively make the holes line up? So if the length and width and height of the box could change, how are we going to deal with the holes? Now, if you look at it, this dimension probably doesn't really matter, right? That could be anything we want it to be, and those holes will still line up. It's this dimension and this dimension. We'll call this the height of the box, and this the length of the box. If those change and the holes don't change with it, they won't line up. So how are we going to keep these lined up? Just theoretically. What do we know about that hole with respect to this kind of flange and that length? It's what? I think I heard it. It's centered, right? So this hole is, no matter what, no matter what length or width we make this box, we want it centered with respect to this length. We also want it centered with respect to that flange, right? We don't want that hole to be kind of right there or up here. We want it centered in that flange, right? What about these holes? We want those holes centered with respect to what edge? That edge, right? And we want it centered within here. So how are we going to do all that? Well, the answer is, if you want something centered, you relate it based on its center line, or if we're talking about centered with respect to an edge, we want it related to its midpoint. Okay? So what we did here, and I should say what Professor Hodgkinson did. So if you go into the male component and you look at its history, you've got the base flange, which builds the male component, and then you've got the cut extrude, which cuts the holes. Okay, if you go into the sketch for the holes, that's the male. Let's exit that sketch. Let's go into the female. Yeah. All right, take a look at this. So in the female part, Professor Hodgkinson he sketched in these lines. So in order to cut extrude the holes, if you look at it, if I hover over the cut extrude, you see that the holes highlight here, and you see a preview of the cut that's going to be made. Okay, and then you see the sketch. So I'm hovering over the sketch. Look at the sketch. So you see these center lines here. Okay, he sketched those in and then related the holes to be on the centers. So if we display relations, we've got a couple of we got a horizontal. So this hole and this hole are always going to be horizontal with each other. So that forces those two holes to be collinear. And then the verticals, you can see this one is going to be vertical. And then we come into the midpoints. These are the important ones. So basically he sketched this line on the midpoint of this flange, which forces the hole to always be on the midpoint of this flange. And then he sketched this line to be on the midpoint of this flange, and this line to be on the midpoint of this flange. So no matter how big the box gets, those little center lines will always be on the midpoints of the flanges. And then when he put the holes in there, he made the holes equal radius so that they're always the same diameter. And he made the center of the hole coincident with the midpoint of this line. So no matter where this line moves to in space, the center point of those holes will be on the midpoints of those lines. Questions? You get the idea here. So to force these holes to be correct, you draw in these midpoint center lines. And then when you go to make that in the assembly, you just make the holes coincident. Any questions there? We can go through that in more detail if you want, but I think that's probably good. Any questions there? Okay. All right. I need my lecture 5 box. Or maybe not. Maybe not. All right. You may have run into this issue in building your box over the weekend or modeling your box over the weekend. SolidWorks does some goofy stuff sometimes. They can't fix everything. I suppose they could, but... All right, so let's open, and you probably found this to be true. When you make changes to your part, it updates your drawing. So I'm going to open this female part, and then I'm going to open the female drawing. All right, here's my drawing. Hey, Zoom in there. Be a good drawing. All right, so a couple things to notice. So on sheet metal, take a look at this. This is kind of interesting. It puts this little notch in here where the flange went. So I don't know if you guys have built your boxes yet. It's not due till Wednesday, I think. But you'll notice when you start bending up aluminum, it's malleable, and as it curves and as you force this bend radius in, the material deforms. And in order to get these things to line up properly and have a place for the material to deform on these bend lines, you have to have some clearance for that to bend up. So SolidWorks kind of guesses at that for you. If you go back to, let me open up the mail as well, and actually the assembly. I got to remember which one it is. Let's see here. I think it's just called box. So if you zoom in real close here, let's take a look at this corner. Notice what's going on here. So it looks clear there, right? That little corner made it in this little guy, in this radius. But that's awfully close. It's really, really close. You could measure it if you wanted to. You could go to evaluate and measure. And you can see that there. Let's see. I think it's the black distance here. Yeah, the black distance there. Look at how close that is. That's 6/1000ths of an inch. Now, do you suppose, even if you had a lot of practice and you were really good at sheet metal bending, that you're going to get that to within 6/1000ths of an inch and get that right? I mean, there's no way. You're bending up material. So that's just not going to fit. If you try and manufacture that, it's not going to fit. Okay, another thing. Look at that. Does that look like an issue? That's not going to work. And remember, you can go into that interference detection and calculate it. And you're going to see all these interferences. Let's see if yeah, there I caught that one. See how it's hitting that bend radius? So, and there's another one where it hits there. All right, so in this case, it's probably okay because it's sheet metal and you're not going to bend it up very well anyway. So you could probably let this go as a solid modeler, but if you wanted to fix this just to make sure that, at least from the modeling standpoint, the engineering standpoint, that this could technically work, you could reduce this, or you could work on this. What I would have done, which I believe I did on mine, is I would have notched this male part out. So let me hide this. I would have cut this kind of, here I'll draw this in. I'll just draw a line so you can see it. I would have cut a 45-degree notch there, and that would guarantee me that I don't have a problem in the corner with the radius. So I would have done something like that, and then, but that doesn't fix everything. You also have to deal with this issue here. It's looking like this face and that face are exactly touching each other. You probably don't want that. You probably want some clearance between the parts, because when you bend this up, you're not going to get it at exactly 90 degrees. You probably want a little bit of clearance in there. So you can adjust your, let me hide this. Hide the female again. You can adjust the distance from this face to this face in the sketch on your base flange for that component in order to bring that width a little narrower so that you have some clearance between the parts. And it'll still work because you're fastening the parts together with screws. So you have some space to work with there. Okay. Another funny thing that SolidWorks does. Let's go to the female part here. So I've got the flat pattern feature, and I've got this cut extrude feature. I'm going to unsuppress this cut extrude feature so you can see what's going on here. What I did was, this is a common technique in sheet metal, to absolutely force that corner to have some room so that when you bend the flanges, that material can malform into place. You can notch out a little hole. Very common for sheet metal people to do this, even if the engineer didn't draw it up that way. I drew it up that way to show you what you could do. You can see how when you bend on this line and bend on this line, that this hole gives it some relief so that the material can come together. But if you go to the drawing, you see it there, right? So that's good. But then I go back to the female part and I suppress that feature. SolidWorks kind of drops in this kind of goofy little notch for you anyway. And that's a function of the sheet metal utilities. So I just wanted to show you that. Another problem is, if I go back and unsuppress that feature, I've got this flat pattern thing going on. If I bail out of the flat pattern up here, that should bail me out. It bends the box up, so it bent the female part up into its correct configuration. I've got a little clearance there, but then when I go to my drawing, my little holes don't show up. So no program's perfect. Sometimes these parts don't move into the drawings correctly. Yes, sir.
There's a way to fix that.
Really? I've never found it.
What you do is you use the unfold command, not unsuppress the unfold feature at the bottom, but the unfold command along the command line. Adjust those features, and then you do the cut, and then you refold, and then it shows up.
Oh yeah, true. Yeah. You can, but then if you want to see it the other way, yeah, you have to go back and do that. Yeah. So you have to decide which one of those you want. In my case, I want my model to be correct, and the drawing can be a little bit off. SolidWorks did suggest a little notch there, so I thought that was okay. If you wanted to tell the machinist, hey, I really want that hole there, I would do what you're saying and unsuppress that feature and show the little hole, and then PDF that drawing to the machinist. Yeah, correct. Yeah, it just won't do both at the same time. No, it won't. You can't have the circles here and then the circles over there.
I think I blew my model there. I'll show you.
Okay, yeah, I mean, show it to me, but it didn't work out. Also, it definitely doesn't work out if you put your isometric view up here. So, did you put an isometric in at all? Yeah. You did? Okay, I'll take a look. Let's take a look. Talked about interference detection. That's good. All right, so along the lines of that interference, I want to talk to you about, and this is less of a SolidWorks idea and more of an engineering type idea. So when you start doing your designs, Does anybody know the difference between precision and accuracy? You should. Go ahead, Anthony.
Precision is like how close the values lie to each other.
Mm-hmm.
Accuracy is how close they lie to the actual value.
To the truth value. Correct. Very good. You'd be surprised how many seniors roll in and don't know that. So, very good. So, the best way to explain that, and it's probably been explained to you this way before, but if it hasn't, I'm going to show you anyway so you can see it visually. Is this. So low accuracy, high precision. So they're all grouped well, but they're not hitting the bullseye. High accuracy, low precision, so they're not grouped well, but they're getting close to the bullseye. And then high accuracy, high precision, they're hitting the bullseye and they're really close to each other. So when we talk about manufacturing, we use the word precision a lot. And it's kind of a misnomer for what you guys are doing here at school, because you're not really interested in precision all that much. Most of the items you're making are prototype type items. You're making one item. So you care way more about your accuracy than your precision. But you get out into the real world, they care about accuracy, of course, but they care about precision a lot. Because if you're making a whole bunch of parts that fit together, and we're talking tens of thousands or hundreds of thousands, and they're all supposed to fit together and be interchangeable, kind of the Henry Ford Model T thing. We make 10,000 cars and then we sell a part. It ought to fit every single car. The precision has to be there, and that's where we move into drawings and tolerancing. Tolerancing has to deal with the accuracy is going to be the desired number, how long your box is, and the precision is going to be the tolerance. You can be off by this much, but not outside that window. And it's an important thing to think about. So, and you as the engineer need to put it into context. So, for example, there's been some questions about these boxes. What would you assign tolerances to on these boxes? So, for example, let's go to the female sheet. What do you suppose, if you were the design engineer, is the most important dimensions in this drawing, in this box, that need to be accurate or precise or both? The hole, what about the holes?
You have to be really
and what about the holes?
They need to line up with the holes on the other part.
Right, so they need to line up. So that's the reality of the situation. But what dimension about the holes matters here? Is it okay if my holes were 20 thousandths bigger on this female part in diameter? Is that okay? Yeah, it's okay, right? The screw will still go through, won't it? Is it okay if they're smaller? The screw won't go through, right? What else is really important about the holes?
Their replacement relative to the holes in the box.
Yeah, the locations of the centers, right? If those locations of those centers are off too much, then the holes aren't going to line up with the other part. So you would want to tolerance that close. Now, remember, the closer you tolerance things, I mean, why not just say, hey, it's got to be 4.44 inches perfect on the money to infinite decimal places. Can you do that? I mean, so you can't do that. There's inherent errors in manufacturing. You've got to allow for some tolerance. The tighter you make that tolerance, what do you think is going to happen the tighter you make that tolerance? It's going to cost more, and why?
It takes more experienced machinist and more time.
More time, more experienced machinist. They might have to make 5 pieces to get one right. Might have to scrap some and throw them out. So you as the engineer need to think, okay, what really matters here? And what can I tolerate precision-wise? So you want to make those tolerances as wide as you can and still have the part work. So you want to make them as big as you can and still have the part work. Now what you can do there in some parts, some matter a lot more than others. So for example, this length. If this length was off, let's say it was bigger by 1/8 of an inch, how does that manifest itself in the parts? If I go back to this assembly and that length of that female part was bigger, what would happen is these little flanges would stick out from the box a little bit, right? Maybe stick down here a little bit and down here a little bit. Is that a deal breaker for this box? We're throwing electronics in there, right? There's going to be a circuit board inside. The circuit board probably doesn't care too much if this little item was a little farther down here. What about this flange? If that's off a little bit, maybe 10 or 15 thousandths, that's not a problem. Maybe even 50 thousandths might not be a problem. Can't be off by can't be smaller than more than the distance from there to there, right? Because then this hole would intersect this edge, and then you won't have anything for your screw to grab onto. So that's the kind of thought process you have to go through when you're dimensioning these parts. Make sure you get the widest tolerance you can and still have the parts fit together and perform the way you want them to perform. All right. Typical dimensions. Typical dimensions. Bad, Professor. I didn't put my dimensions in. I know why, because this is Professor Hodgkinson's drawing, not mine. Typical dimensions for, there's typical tolerances that you can hit for different machines. So if you're using a bandsaw, you're probably only going to be able to get within maybe 1 millimeter at best. So that's about 40 thousandths of an inch. And that's if you're really careful when you saw that out. Not a very accurate or precise cutting method. Our milling machines and our lathes, standard milling machines and lathes or conventional milling cutting tools, you can pretty much trust that they're with a competent machinist and reasonably good quality tools, you're going to get plus or minus 5 thousandths of an inch. That's not that hard to achieve. Okay, so if you just kind of want a blanket tolerance for the whole drawing, plus or minus 5 thousandths is probably not going to hurt you. Plus or minus 10 thousandths, pretty easy. You can hit those pretty easy. What you can do is if you don't really care about a whole bunch of dimensions and there's only 1 or 2 supercritical dimensions, which you can, there's a couple of ways you can go. First, you can say, okay, you can have a blanket or a global dimension on your drawing for 2 place decimals, and you can say, hey, let's make that plus or minus 10 or plus or minus 15. And then when you go to your drawing, you can say, okay, any 2 place decimal, I'm okay with that. And then you can tighten up your 3 place decimal and say, I want that to be plus or minus 5 thousandths of an inch. And then these dimensions that you really care about, like these hole locations, you can make those 3 decimal places. That's one way to do it. Another way to do it is to have your global tolerances, and then if you really only cared about one little dimension, you could call out a note, and you can, in your drawing tools, you can go to annotation, and you can say note, and you can say, hey, I want that one right there, and you can write in your note. you can write its own tolerance. You could say, for that right there, I want it to be, maybe I want it to be that circle that you're going to show me how to do. Maybe I want that circle to be plus nothing minus, or minus nothing plus 15 thousandths of an inch. So you're telling the machinist, hey, it's really important that this thing be either at this or bigger. Bigger's okay, but smaller's not. Okay, so you can do that with individual dimensions in your drawings. So don't be afraid to use that. Now, you don't want to get crazy. You don't want to dimension that, 20 of these things all over the sheet. At that point, just make the whole sheet that tolerance. You want these sheets to be kind of clean looking. This one looks pretty clean, and it's probably good enough. It'd be nice to see the isometric view to tell the machinist how this kind of looks. I think he'll get the idea, but it just makes it cleaner and easier to understand, especially when you're presenting it to people. If you had to present a drawing for some reason, it's nice to have that isometric view. Okay. I think we've already gone over measurement tools and which ones we would use. All right, drawings. We're gonna do a few more things about drawings. Now you guys have probably figured all this out. I kind of screwed up. I told you to do. I required you to do drawings, and I didn't lecture on drawings. I was assuming we were going to make it through the lecture, but we didn't. But I bet you figured it out. This particular class, and probably any class you would take here, we're not churning out draftsmen here. In the old days, they didn't have computer aided drafting, so literally people had a job, and all their job was to make drawings. They still have those people, but they need to be kind of cross-trained a little bit. The design engineer has to work closely with the draftsman, so the draftsman typically is an engineer nowadays. So you can go out and get an engineering job drafting all day long. It's more fun to build or design the components and then test them, but you can get a job drafting, and you'll be doing it with CAD tools. But we're not here to make you draftsmen. What we do want to do is make sure that you can communicate your designs well, which requires at least a rudimentary understanding of the drawings and the tolerances involved and what you should be calling out. The other problem for you engineering types, we're a little bit different here in school in that we're not your typical machinists. We understand the program, and we do engineering as well as machining, and we're college educated people. When you get out into the world, your machinists are not going to be that. Okay? They're probably don't have a college degree. They're very single-minded, narrow-minded, and they're going to take these drawings, and rightly so, that's their contract with you. So they're going to build the thing exactly how you show it on the drawing. If you're missing a dimension, they're just going to say, I can't build this part. Instead of coming back to you and saying, hey, you're missing a dimension here, which is what we'll do with you. Okay, they're just going to say, no good, reject. Okay, so a lot of times big companies will have a manufacturing engineer that can deal with that kind of machinist mentality and can also deal with the engineer that forgot to put the dimension on there. And then that manufacturing engineer can deal with both personalities and interface between the two of them. If you're in a smaller company, you're going to have to be that person. So just be aware that machinists are different cats. All right. Drawings. Let's go over a few things about drawings. Let's go back to that. Let's do a better drawing. Do I have a better drawing? These are Professor Hodgkinson's drawings. I don't think I like them. How about this one? Oh yeah, this is a Professor Road drawing. Okay. All right, as said before, and as you saw in some of my comments back on your grading, the title box is really important in drawings. So you know, it's important to you to have who you are and what the part number and what your box is, but it's also really important to have the material, the tolerances, how you want the machinist to finish this part off. That's not always evident. You want to make sure you're deburring edges. There's something I'm missing here that if I went back to do my template, I would put in quantity. How many of these things do you want? So I would have put a quantity box in there. I probably should have put that in there. So your title box is important. You don't want to obscure the whole drawing if possible. You want to keep your drawing area as clean and open as possible. So try and make your title boxes as small as they can be, or position them such that they make some sense. It's kind of conventional to have them on the bottom right-hand corner, but not necessarily true. You can have those anywhere you want. Sheet size. Sheet size is important. So this is, it took me years out in industry to figure out what they meant by the sizes. This is what's called an A-type sheet. So that's an 8.5 by 11 inch piece of paper. A lot of drawings can fit on that. But a lot are so complicated and there's so many dimensions and so many views that it can't fit on an A-size sheet. So they have B-size sheets and D-size, C and D and E. So I wanted to show you some of the sizes. So for example, these are real parts. These are from our BioSurf Center. It's kind of a bioastronautics type center. These are real parts they have built. This is a D. That's a D-size print. Okay? And you'll notice, you can see, this was a complicated enough part that they felt like they needed to have some specialized views. And you couldn't fit all that around. So go ahead and you can pass those around if you want. Here's an E-size sheet. You get really complicated, you do one of these bad boys. That's an E-size. Alright? Look at a couple of those dimensions, you know, while you pass that around. Just look at them, they're kind of neat. So I just wanted to get you guys a feel for how big those are. Views. So I'm going to open my Lego part. Lego my Ego. Alright, so you'll notice here, on most drawings you'll need a standard 3-view drawing. So imagine this one's not here. This is your standard 3-view. You got to at least have that usually. Okay? There are times when a part is so simple, say like a cylinder, that you only need 2 views. But for your standard, you know, rectangular-ish part, you need 3 views. One convention that you must know about views, and you must not screw up, because you can force SolidWorks to screw this up. Don't do this. You need to know that when you go between views, you should think of your part like it's in a cereal bowl. So if my part was in a cereal bowl, imagine I've got my bowl here, and you're looking at this side of that part. To get to the next view up here, pretend like you're sliding the part up the side of the bowl. So that's the view I'd be looking at. Okay? Now what if I wanted to go down, up the bowl? So now I'm looking at this. Okay? If I want to go the other way, up the side of the bowl. Up the side of the bowl. Okay? So my Lego, here's my Lego. I'm looking at that side of it, up the side of the bowl. Is that correct? Up the side of the bowl. Now I'm looking at the bottom. Up the side of the bowl, I'm looking at that end. Got that? That's an important convention that most people miss. Okay? So that's good to know. Isometric views, they're very useful for kind of understanding what the part looks like in 3D. In this particular case, I put 2 in because this doesn't really tell the whole story, does it? So I kind of, in this particular case, I wanted 2 to kind of tell the story. You don't always need that. Isometric views are for reference only. They don't really give you all the information you need. So it's just to get a general idea of what's going on. So you don't always need to have these. You do have to have your standard views though. Most of the time you'll see do not scale because sometimes machinists will actually scale the drawing. Sometimes you want to do that. One good example is, oh, did I close that? One good example is your sheet metal parts. Now this isn't a very standard method of manufacture, but you could have used it. So if your particular box fit on any kind of sheet of paper that you could print out, especially if it's 8.5 by 11, because those are all over the place, right? But if you could find a large size printer like my plotter there, you could actually print it out to scale and cut it out and tape it to your aluminum and then mark all your holes. Save you a lot of time. Be kind of cool. All right, so, and in this case you could do that because that would be close enough for the purposes of the box. That's not a real common thing to do, but you could do that. So sometimes you can scale the drawing, but most of the time you can't. So just an idea there. What else do I want to talk about? Projected views. If you notice, if you insert a drawing view, I'm sure you guys saw this, but you can project views from, let's see, I have a draft quality. Let me open up another part. Let's just do the part. When you make a drawing, you can either open a new drawing or you can say make drawing from part, just like you can make an assembly from a part. I'm going to use my custom template. You can start dragging in views, and then as you drag, see how it drops them in? It's kind of cool. So those are your projected views. We talked about your standard 3 view. Where are we at here? So here's my standard 3 view, and I felt it necessary to drop in another view because I just wasn't conveying the information well here. Another thing is, did I really need to show these hidden lines? I think if I had to do this over again, I probably wouldn't show these hidden lines. It's irrelevant. You can see them here. And it's pretty clean to see here. So you want to be careful. You don't want to duplicate too much stuff. It keeps your drawings cleaner and it makes it easier for people to find things. I could show you some really terrible drawings that have every dimension on the sun on there, but if you wanted to just find one, you can't find it. It's really irritating. So you want to keep these clean. Auxiliary views. You might want to do different kinds of views, like your isometric. Section views. There's a section view on those prints I sent around for you. Section views are kind of cool. So a section view will basically cut your part in a certain spot. This becomes very useful when you have parts that aren't symmetric at all. So this part's fairly symmetric. You've got, you know, the 3 nice little guys there. But what if you had one post here and one post up here? you might want to cut this piece right there and show the view somewhere and show just that section. One thing to note is take a look at on a sectional view, it'll tell you what letter the section is. It'll show you the arrows, and that's basically telling you, hey, this view is me looking at this direction from these, or looking at the part from this direction following these arrows. So that's what you're going to see here, and that should make some sense. Then it goes ahead and cuts this part as if you cut it with a bandsaw and lets you take a look at it cut in half. That's a particularly useful view. Detail views are kind of cool. These are really useful typically on the corners of parts. So a detail view, if you wanted to do, just look at, I kind of screwed that up, but let's go with it. It kind of zooms in, see, and it just cuts that section of that out, and then you can see that better. So in this case, that's where I'm really getting hurt by the hidden lines. That's getting too crowded. But those are kind of cool views to use, especially at a corner or a little tip of something if you want to show that. Break views. Let's do a break view. Where's my break view? Oh, it's not showing it.
Maybe you have to select the drawing for that to work.
Yeah, I might. Let's see. There it is. Okay, this one's not going to make much sense, but a break view, so there's the break line. Let's say I break it here. And you have these options. You can do straight curve, zigzag. Let's just keep zigzag. This drawing's getting too crazy here. Why didn't it show me a break view? Let's open a different drawing. I should have closed this out. I should have made you a good drawing of a part that makes sense for this. Alright, so there's my break view. So I broke this in half, or close to half. So this makes no sense to do it on this Lego. Where it does make sense is if you had if the aspect ratio of your part is very high. So let's say you had a piece of all thread. Let's go back to that rocket project. Okay, they had these long pieces of all thread that were probably 3 feet long, but they were 3/8 in diameter. If you put that on a drawing, you're going to have this 3 foot long thing, and it's going to look like a tiny little thin line on the drawing. So it's not going to really give you an idea of what that part is. So you want to use that break view. Instead of having that entire 3 feet, you can use the break view and just have a little section of it. So you can put a nice big diameter, on the page. It's going to be like an inch or 2 or something, and then you can dimension that to be 3/8 of an inch. You put your break view in there, and then you dimension from the left to the right and say it's 3 feet long. The break view tells you, okay, it's 3 feet long, but we're not showing all that on the drawing. So high aspect ratio parts, that's a useful view. All right, I showed you the annotation toolbar in your drawings. There's a lot of good stuff here. You can put balloons. You can put surface finishes if the finish is important. That becomes important for like bearing presses or linear bearings, or something that you want pretty, or something that you don't want to have maybe you want to call out a poor finish because you're going to adhere two parts together. So you want some really bad inconsistencies in there, which will increase the surface area, and then your adhesion will be better. So you can use those surface finishes. Center marks, those are useful. Center lines. There's all kinds of stuff here. The notes are really good. I like putting notes in there. Some of the symbols. Where's my symbols? There's some really good symbols. Okay. All right, so you go to these symbols. A lot of these are really cool. So this one's diameter, obviously degrees, plus or minus you're going to use quite a bit. Center line helps. This little symbol is how deep do you want to go? So that's really useful for holes. This symbol is called counterbore. So you'll call out a hole and say, hey, counterbore it this deep. And so that you can stick a head in there of a screw. And there's a whole bunch of other ones. So you might want to check, just read all those and take a look at the different types of symbols you can use. They're interesting. And then real quick with the last minute here. Oh, no, I got to show you this. Why do I keep closing these things? Stop closing these things. Oh, actually, I'll do it here. Ordinate dimensions. These are some of my favorite. Instead of smart dimensioning, I like to ordinate dimension. And that means coming off of one datum. That's really useful for something like this Lego. So you can click the one edge, and that says I'm 0. And then you can click this center line, and that tells me I'm there. I'm that far off of that datum. That center line, I'm that far off of that datum. That center line, and that center line. You see how that looks so much nicer than, let's go there to there, and let's go there to there, and let's go there to there. I mean, that's pretty ugly. This looks much better. So ordinate dimensions are pretty cool. And then the last thing I'm going to say is geometric dimensioning and tolerancing. I don't like it. Now it's out there in industry, and geometric dimensioning and tolerancing is there to convey kind of the intent that the engineer determined, rather than the actual dimensions. I prefer having the actual dimensions, 1 inch plus or minus 5/1000ths of an inch. I like to just say that right there. Okay, that's a standard dimensioning technique. GD&T would say this hole needs to be this big, and don't make it any bigger or smaller for a 440 screw. So that conveys intent, and it's useful, but I like to tell the machinist, hey, you got to hit this window. Okay, so we're not going to go into GD&T, at least not for aerospace engineering and not for the curriculum here. All right. Any questions related to drawings?